All right, everybody. This video, I'm going over a worksheet that goes over chemical kinetics. So in my AP chemistry classes, we do kinetics. It's our unit 7. But I got this worksheet from one of the students I tutor. It's a worksheet that their teacher uses. And it's a good worksheet to go over the basics of not everything that goes on in our unit 7. But a lot of things, especially like kind of the introductory things when it comes down to chemical kinetics, that's what this worksheet will cover. So all I am doing is going through this worksheet on chemical kinetics and just showing you the answers and just explaining a few of the things for you. All right. So in fact, I like this worksheet so much that I'm probably going to assign it to my students once we get to Unit 7. All right. So let's dive into the worksheet. Okay, so here's our worksheet. So it gives us, how to interpret these graphs, why are the slopes of the lines different? Then we have some time versus concentration data, what we can do with that. It gives us this data where it gives us our rates and different concentrations and how changing the concentration might have affected the rate of the reaction. And then on this side, we got our potential energy diagrams or our reaction coordination diagrams and what happens there. And then here we have reaction mechanisms. So what can we get from reaction mechanisms and some things that like knowing some different terms like what is an intermediate in a reaction mechanism, what is a catalyst in a reaction mechanism, if there is one, and that kind of thing. So anyway, let's just go through these one at a time, and we'll talk about what's going on with chemical kinetics. All right, so remember, kinetics is the study of how fast reactions go. It's the study of the rates of the reaction. And a way that we measure the rates usually is how the concentration of the different components of the reaction change over time. So we could look at how fast the reactants are consumed, or here we could talk about how fast the products are produced. But we also want to understand that there's a stoichiometric relationship here. So for every one hydrogen that is consumed, you have to lose 2 ICLs. Or for every 2 HCl's that get formed, only 1 I2 gets formed. Okay, so if I know how fast this is forming, then all it is a little bit of stoichiometry to figure out how fast that is forming. If I know how fast this is disappearing, then all I have to do is multiply by 1/2, and that'll tell me how fast that's disappearing. Okay, so in this question, we have curve A, curve B, curve C, curve D, and it's concentration versus time. So as time moves forward in this reaction, it's what's happening to the concentrations of everything. And we have to identify, which of these components, H2, ICl, HCl, or I2, curve A represents, curve B, curve C, curve D. All right, so let's scroll on down to my key here, and we'll get to it. Okay, so the first thing we should know is the curve for A and the curve for B, those would represent reactants. Because if you think about it, at time 0, you only have reactants and you don't have any products. So the reactants have to react to form the products to get any products. So at the initial time, you're going to start with a lot of reactants, and as you approach equilibrium, you're going to lose reactant. You're going to start with 0 product, and as the reaction approaches equilibrium, as you lose reactant, you gain product. So the products are always going to start at 0 and increase, and the reactants are going to always start at their highest number and then decrease. Okay, but if we go back to the worksheet here, we're losing A at a slower rate than we're losing B. All right, so that should tell us that A is H2 and B is the ICL, because I lose 2 times the amount of this compound for every one of these. So for every one of these molecules that is consumed, 2 of these are consumed. So you're going to lose this faster than that. So B is a faster rate of disappearance. So B should go with the highest coefficient on the reactant side. And A is a slower rate of disappearance. So A would go with the one with the lower coefficient on that side. Okay. So again, reactants get consumed as the reaction proceeds. So A is going to be H2 and B is going to be ICL, because we should be able to look at the equation and see that I'm going to lose two of these for every one of those. Okay. And that means C and D are the products. Okay. But what's going to be true about their rates? Okay. Well, we're making C faster than we're making D. So let's look at the coefficients. Okay. We're going to make this HCl faster than we make this, because every time we get one of these molecules, I2, we get two of this. So we're going to make this twice as fast as the I2. Okay. So for our products, the HCl is going to be the one that's producing faster. So that's going to be curve C. And the I2 is the one that's being produced at a slower rate. So that would be curve D. Okay. So we got, again, curve A would represent H2, curve B would represent the ICL, curve C would represent the HCl, and curve D would represent the I2. Okay? All right, so let's go to the next problem. All right, so in this problem, whoops, we have this reaction, and we are given this data. So the concentration of how the concentration of O3 of ozone changes over time, and it just gives us the first 3 seconds of the reaction. And this is how the O3 is decreasing with time. Okay, and so from this data, we just want to get the rates of disappearance for O3 and the rate of appearance for O2. So the first thing I'm going to do is, because the data gave me directly what was going on with O3, I'll figure out the rates of disappearance for O3. And then once I have the rates of disappearance for O3, all I have to do is multiply by the ratio, 3/2, to get the rate of appearance of oxygen. So what we're going to do to calculate the rates is, in this case, they want concentration over time. And so what it really is the change in concentration divided by the change in time. Okay, so if we look at the data, let me go back to the worksheet here, and I'll zero in. The first rate we're looking for is 0 to 1 second. So the change is going to be 0.1 minus 0.091, and the change in time is 1 second. Okay, so we go back to our work. I'm going to do the difference between 0 seconds and 1 second, and I'll divide it by the change in time, which is 1 second, and that comes out to be 0.009, and the units would be molarity per second. All right, so the rate of disappearance, this is how fast we're losing ozone between 0 and 1 seconds. All right, and then if we look at the next part of the chart, we want to know the rate from 1 second to 2 seconds. So now we're using these two data points. So we got to figure out that difference and divide it by that difference. Well, the difference in time is still just 1 second. So we just got to take this difference and divide it by 1, and that will give us our rate for O3 at for the second part of the chart. Okay, so again, I'm doing the difference between 1 second and 2 seconds, and I get 0.008. So notice the rate of disappearance is decreasing as time goes on, and that's because as we get less and less ozone, we have less particles for the reaction to occur, so the reaction is going to occur more slowly. So the rate of the forward reaction is always going to be the fastest at the start of the reaction, and as time moves on, it's going to slow down. And the rate of the forward reaction at time 0 is always going to be 0. It's going to be the slowest because you don't have any products. But then as the reaction proceeds and you make more and more products, the rate of the forward reaction will start to increase. All right. But that's really not what the question's asking about. It's just figuring out those rates. Okay. So understand. So in my chart, I have these two rates. Now, what I could do is do the stoichiometry to figure out the data table for oxygen to see if I lost X amount of O3, how much O2 was consumed, and I could do that. But really all I need to do is see that the ratio of O2 to O3 is 3:2. So if I take these rates that we calculated for O3 and I just multiply it by 3/2, that'll give me the rate of the other thing in my equation. In this case, the rate of appearance of oxygen. Okay, so all we have to do is take our rates from the original that we calculated and multiply it by the mole ratio that we're comparing, or coefficient ratio. And so the numbers that go in here are 0.0135 for the rate of appearance for O2 in the first section, and then 0.012 molarity per second there. Okay? All right. So if we look at the next question, okay, and there's two questions 3. There's this question 3, and then there's the question 3 on the back. So the first question 3 on the worksheet, okay, we have this equation, and we're given this set of data, and the first thing we have to do is figure out the rate law. Okay, so what we're going to do is we're going to have to understand what does it mean to find a rate law. So this is what we're looking for. All right, we're looking for this. Rate equals K, lowercase k, that's the rate constant, times the concentration of each reactant raised to what we call their reactant orders. So what we need to do to find the rate equation is, all we have to do is figure out what X and Y are here. We have to figure out the order of the reaction with respect to this reactant. So what is this reactant's order? And the order of the reactant with respect to this. Okay, so we have to find the individual reactant orders from this data. Okay, so we're figuring out X and Y. And then once we figure out what X is and what Y is, all we have to do is put those numbers there and then write the rest of it. And just as soon as I figure out that number and that number, that's what we're looking for in part A. So find the rate law for this reaction. All we have to do is figure out what X is and Y is and write that down. That would be the rate law. Okay? So usually the reactant orders are going to be 0, 1, or 2. So a reaction can be 0 order, a reaction can be first order, or a reaction can be second order. Okay? A reactant. Okay? And the way you know is if a reactant is first order, let's do 0 order first. If you change the concentration of that reactant, but the rate doesn't change, then that's 0 order. So if changing the amount of the reactant doesn't affect the rate of the reaction, then you have a 0 order reactant, okay? And if it was 0 order, you would, like, let's say H3 comes out to be 0 ordered. If that comes out to be a 0, then you wouldn't even include this in the equation because anything to the 0 power is 1, okay? So if a reactant isn't included in the rate equation, you know it has to be 0 ordered with respect to that reactant, okay? All right. But usually reactants are going to be either first or second. And so first order is whatever change you make to the concentration of the reactant, if the same thing happens to the rate, then it's first order. So for example, if I double the concentration and the rate is doubled, then I have a first order reactant. If I quadruple the amount of concentration and the rate also quadruples, that would be a sign that it's first order. If I cut the concentration in half and the rate of the reaction cuts in half, then it's first order. Okay. Second order is whatever change I make to the concentration, if the same thing squared happens to the rate, then I'm second order. So for example, if I double the concentration, but the rate quadrupled, 2 squared, then it's second order. If I triple the concentration and the rate got multiplied by 9, which is 3 squared, then that would be a sign that it's second order. Okay? So based on this data table, we're trying to figure out each reactant order. That's what we're trying to figure out. Okay. So to figure out the reactant order for pH 3, so to figure out X, the reactant order for pH 3, we should look at trials 1 and 2. The reason why we're looking at trials 1 and 2 is because between trials 1 and 2, we changed the concentration of pH 3, but we kept the concentration of O2 the same. Now, what does that mean? It means anything that happened to the rate is due to this change. We know that the amount of O2 didn't affect the rate because we didn't change it between those trials. So if I'm looking for this reactant order, I'm going to look at these 2 trials because it's where I changed that particular reactant, but I didn't change that particular reactant. Okay? So what did we do? we doubled the concentration. We went from 0.1 to 0.2. And what happened to the rate? It doubled. It went from 2.1 to 4.2, both times 10 to the negative 2. So the rate also doubled. So we doubled the concentration and the rate doubled. That tells us that pH3 is first order. So this X is a 1 in my rate equation. Okay? So we just figured out, so looking at trials 1 and 2, we doubled the concentration of pH3, we kept the concentration of O2 constant, and we noticed that the rate also doubled. So that means pH3 is first order. So we have our rate equation, and it looks like this. I know that. Now all we have to do is, again, using the data table, figure out O2's reactant order. Okay? So if we go back to the data table, we're going to use trials 2 and 3 to figure out O2. Why? Because we changed, between 2 and 3, we changed the concentration of O2, but we kept the concentration of pH3 constant. So that means whatever this changes to the rate, whatever that change is due to the change in O2 and not due to the change in pH3. Okay? So 0.1 to 0.3, we tripled the concentration, okay? But we got 4.2 to 38, right? We got 4.2 times 10 to the negative 2 to 3.8 times 10 to the negative 1, okay? So if I do 0.3 divided by 0.1, I get 3, so we tripled the concentration. But when I do this number divided by that number, guess what I get? I get 9, which is 3 squared. So that's telling me that oxygen is second order. So let me go and kind of explain that, all right? So again, for the oxygen, we're looking at trials 2 and 3. We tripled the concentration of O2. We kept the concentration of pH3 constant. So if I did 0.3 divided by 0.1, right, that's me tripling the oxygen. And then dividing the rates by each other, the rate got multiplied by 9, which happens to be 3 squared. So that's telling us that oxygen is second order. So the answer to 3A is that. Now 1's understood, so you don't really need the 1 there, okay? But we needed to figure out the reactant order of that and the reactant order of that. And we did that, and now that's the rate law, okay? So now if we look at part B, and this usually follows questions like this in kinetics questions, is once you figure out the differential rate law, which we just figured out here, okay, is figure out what K is, but also include the units, okay? Also include the units. Remember, for equilibrium, when we solve for the K value, the equilibrium constant, which is capital K, we don't usually report units for that. But for the rate constant, lowercase k, we will have to include the units. But there's a shortcut in figuring that out, all right? So the first thing to do to figure out the units of K is just take the rate equation that you just solved for, take data from one of the trials. I took data from the first trial. So I took, if you go back to your data table here, I just plugged this data into the rate equation and solved for K. Because we have the rate, we have that concentration, we have that concentration. We now know what X and Y are, so the only thing we don't know is what K is. So we're just plugging in and we're solving for K, all right? So I took the data from trial 1, okay, plugged it in, and I solved for K, and K comes out to be 2.1. So that's the value of K, but you also have to include the units. So for kinetics, the units of the rate constant, a shortcut to remember is the units of K will be 1 over molarity, but molarity will be raised to what we call the reaction order minus 1. So whatever the reaction order is minus 1. You're going to raise molarity to that power. So it'll be like 1 over molarity squared, or 1 over molarity cubed, or it might just be 1 over molarity. And then times the unit of time, okay? Now the unit of time for this question was seconds. If you go back to the data, the rate was molarity per second. So the unit of time I'm using for the rest of this is going to be seconds, all right? But sometimes I've seen it molarity per minute. So if you see minutes here, then that would be the unit of time that you would use, okay? So how do you find reaction order? It's really easy. Reaction order is the sum of the reactant orders. So the one reactant order was 1, the other reactant order was 2, so the overall reaction order is 3. So if we plug our reaction order, which in this case happens to be 3, into our units of K shortcut, we get 1 over molarity raised to the 3 minus 1. So that's 1 over molarity squared times 1 over seconds. So you could write the units this way, but understand that you might see the units written this way, right? 1 over molarity squared is also molarity raised to the negative 2. 1 over seconds is the same thing as seconds to the negative 1. Now, the other way you might see it is molarity is moles per liter, but 1 over molarity is liters per mole. 1 over molarity squared is liters squared over moles to the negative 1. So I just realized my key is incorrect here. This negative 2 should just be a 2. So this should be a 2. All right, it should be liters squared times moles to the negative 2 times seconds to the negative 1. So please, if you're going to do it this way, it should be liters squared, not liters to the negative 2. It should be liters to the positive 2 times moles to the negative 2 times seconds to the negative 1. Okay, so again, the value of K is correct. Just realizing I totally messed up the key. It should be liters squared times moles to the negative 2 times seconds to the negative 1. That should not be a negative 2. This should be a negative 2, and this should be a negative 1, but this should be a positive 2. All right. So again, this is fine. It's just this negative 2 should be a positive 2 for the right key. I'm embarrassed by my mistake there. Sorry about that. All right. All right. So that's K, and then that's the units of K. All right. Now, for trial 2, it says, what is the rate of disappearance for pH 3? So all we have to do is see what we were given. This is the rate of, for O2, this would be the rate of disappearance for O2. We would say disappearance for reactants. And so it's asking for the rate of disappearance for pH 3. Well, in trial 2, this is the rate of disappearance for oxygen. So all we have to do is take that rate and multiply it by 2 over 4, and that will give us the rate of disappearance for this thing. So remember, if you have a rate for one of the things, and it doesn't matter if it's rate of disappearance or rate of appearance for a product. If you have a rate of one thing, all you have to do is multiply that rate by the mole ratio, by the coefficient ratio in the equation to get the rate of the other thing. And so, like, let's say I wanted the rate of appearance for P2O5 for trial 2. Well, then all I would do is take the rate of disappearance for oxygen, multiply it by 1 over 4, and that would give me the rate of appearance for this, because I'm losing this 4 times faster than I'm gaining this, and that's what the coefficients are telling me. Okay? So all we would have to do is take our rate of disappearance of oxygen from trial 2, multiply it by our coefficients. Our coefficients for pH 3 was 2, our coefficients of oxygen was 4, so multiply it by 2 over 4, and that gives us the rate of consumption or the rate of disappearance of pH 3 for the same trial. Okay? All right. So let's go to the next one. All right. So these potential energy diagrams, okay, the hump diagrams, remember you'll see them 2 different ways basically. You'll see it like this versus this. Remember, it goes reactants. This is called the activated complex, and this is the products. Reactants, products, right? The beginning part of a reaction is the reactants, the end part of a reaction is the products, and the intermediate or activated complex is in between. All right. This way, when the products have more energy reactants, that's endothermic. Okay, and if it was this way, energy was lost. We had higher energy here, and then we went to lower energy here. That would be a release of energy. That's exothermic. Okay, so just right off the bat, I can look that this is higher than that, so this would be an endothermic reaction. Okay. Okay. So the first thing is label the activation energy. The activation energy is the energy of the reactants to the top of the hill. So that right there would be the activation energy of the reaction, and the symbol for that is EA, E activation. Okay, the energy of activation. Now, we could do it for the reverse reaction. The products of the forward reaction are the reactants of the reverse reaction. So if we went here, if we went from this energy value to the top of the hill, that would represent the activation energy of the reverse reaction. Right now, we're just talking about the forward reaction, and I think they didn't have a reversible arrow, so right now we're not worried about the reverse reaction because this is only the forward reaction. Okay. All right. So the delta H is the energy difference from products minus reactants, and so this delta H, this particular delta H would be positive because you would do always for the delta H, you would do final minus initial, products minus reactants. So this number is bigger than that number, so you would end up with a positive value, right? If we go back up here to an exothermic reaction has a negative delta H because the products number is lower than the reactants number. So if you do products minus reactants there, you'll end up with a negative delta H, okay? All right, so that would be the delta H for the reaction, okay? What a catalyst does, a catalyst doesn't change the end of the reaction, it doesn't change the products, and it doesn't change the reactants. It only changes the activated complex. It lowers the activation energy. So the dotted line would show the effect of a catalyst, okay? What does it do? It lowers the activation energy. And then when we add a catalyst, it really wouldn't change the curve too much. You would get more overall molecules because you added a catalyst is made of molecules, so you would end up with more overall molecules. So the area under the curve might get a little bit bigger, but the curve distribution would look pretty much the same. It's just we would take the activation energy that was kind of over here, and we would lower the activation energy to here. So now more molecules have enough energy to overcome the activation energy. So really, if I go back to this chart here, all we're doing is we're moving the activation energy down a little bit. So now we have more particles that have enough energy to overcome the activation energy. So I took this activation energy and I just kind of moved it down a little bit to answer number 4 there. Okay. All right. And then, okay, if we look at the reaction mechanism, all we have to do is add up these equations to get the overall equation. And so what we should notice is when I set these up, if two of the same thing are on opposite sides, they cancel out. So the HOI here cancels out with the HOI there. The two hydroxides end up canceling out. And then so what we're left with is one of these plus two I's. Whoops, I'm missing one. Plus two, I should have two H3O pluses on this side of the equation as well. Sorry, I didn't write those down. And then that yields one I2 and four, and that should be four H2Os here. So, sorry, the key's wrong again, but this is two hydroniums should be here, and a coefficient of 4 should be there, okay? But I did the work right here, I just didn't come up with the right answer there. Just rushing through it, okay? So again, two hydroniums there, included on the reactant side, and this should have a coefficient of 4 there, right? So that would be the overall equation, okay? Now, when you want to identify intermediates get produced, then consumed. So they don't start off in the mechanism, they show up on the product side, and then they get canceled out on the reactant side. So they get produced, and then they get consumed in a subsequent step. So they cancel out on this diagonal. All right? So we have two intermediates here, HOI and OH minus. Okay, there are intermediates. Why? Because throughout the mechanism, they get produced first, and then they get used. And overall, they cancel out. Now, in this particular mechanism, there was no catalyst. How do we know? Because a catalyst does the opposite. A catalyst is used first. It starts out on the reactant side first and then gets produced. A catalyst gets canceled out, but it gets canceled out on this diagonal, An intermediate gets canceled out on this diagonal, okay, if you can see my cursor. Catalyst on this. So we had nothing that canceled out this way. So we didn't have a catalyst in this reaction. We had two intermediates, but only one catalyst. And then it says, draw a potential energy diagram. So when you have a multiple step mechanism, you want to show 3 different humps. Now the first hump should be the biggest hump in this case. Why? Because they said the first step was the slowest step. The first step was the rate determining step. And you can only be as fast as the rate determining step. So what does that mean? It means the first step has to be have the highest activation energy. That's why it's the slowest. Okay, and then the last thing is it had to be exothermic because we were told it was exothermic. I think, where were we told that? Oh, yeah, it says right here. It says for this exothermic process. So that means this line at the end, the products area, has to be lower than the reactants area. Okay? So again, if we looked at that first diagram, that they showed us, this is an endothermic reaction because this was higher than that. But they told us this reaction was an exothermic reaction, so you have to show that this is lower than that. So the first hump has to be the biggest because it was the slowest step, so that means it has the highest activation energy. And the second step, so if, for example, in the mechanism, if they said the second step was the slowest step instead of the first step, then if the second step was the slowest step, this would have to be the biggest hump, right? Because the slowest step has the highest activation energy, right? That's why it's the slowest step, all right? Okay. So again, sorry about the couple of typos on the answer key there, but I explained it in the video, so hopefully that's good, all right? And hopefully that helps. And yeah, have a wonderful day. All right.